Okay. So here's, this is for the fun, before I start the more serious stuff. Let's say we're talking about local networks, 1 million neurons, as I said, then maybe 1,000 local connections. So in the human cortex, for instance, there are probably more like 5,000 connections, but multiple connections per neurons, and also not all of them are local. So conservative, I'd say only 1,000 of them are local connections within the network per cell. So that's again to warn you that when I talk about number of connections per neuron, I mean the connections that are within the network. Okay, so then let's say order of that, it will be 1,000 memory items stored. Now in cortex, there are 10 billion neurons. Let me assume that 1/10 of them are devoted to this memory stuff. So you have 1,000 local networks like that. So you have 1 million memory items. I think it's pretty good. I mean, depending what item means. So for instance, in the dictionary, I think English will have like 80,000 words or and so on. So this is, I don't know. Yadin claims that we don't need so much, and he may be right. So I'm not sure that this is just for fun. I don't think we are at the stage that this is meaningful, even functionally or anatomically. So what I'll talk is more about the local network, but that's just for the fun of it with number games. Okay.
Hi.
Yes.
As mentioned, I would give the number of local connections per cell much higher than 1,000.
Yes, I know, but I'm saying I don't think that. I think most of them will not be the local one in cortex. They will be connecting long-range connections, and they will. I think so, and they will have. Also subcortical and so on. And there are also multiple, so the number of boutons is not the number of connections because there are multiple contacts per pair of neurons. And I think if you take this is a more conservative number, but again, we can discuss it. It doesn't really matter so much. If it's, well, 1,000 or 3,000, then it's 3 million here. Yes?
It means that there is a limit for memory, right?
That what?
There is a limit for memory.
Any physical system has a finite capacity of memory, okay? And our brain, maybe it's bad news, but our brain is a physical system and therefore has a finite capacity of memory. Just the question is where we are in this order of magnitude. If you look at popular and semi-popular press, you'll find that we have the brain, human brain has a virtually infinite capacity. And partly the reason is that they say, well, one connection is actually an analog quantity. They can have multiple or many states, or you can store many more bits information in each connection in synapse. If you look at realistic models of information encoding in networks, it's not so. You have 1 bit or less of information per synapse, even though the synapses are analog, like in my model. So it's not infinite, okay? Whether this is something that we have to worry about or not, I don't think we have to worry about.
You're assuming that your 1,000 memory networks, they are not talking to each other, right?
That's right. So that's related to what that question. How do we view the long-range connections? So now if we talk about associations between modalities and so on, then we really have to include into the game information encoded in these long-range connections, possibly. So I didn't do that here. So this is a more difficult, and maybe this afternoon we'll talk about it and so on. No, but it's a more difficult thing to estimate. Yeah, but you're right. This is a very important information-bearing apparatus in the brain, in cortex. Yes?
Our first questions that we were operating on the base between neuron I and neuron J.
Yes.
We have compared the new value of SI&J to F, the average. Why should we do that? Because when SI and SJ are 0.
Yes, so what is your name? Mardi? Mardi. Okay. So you're raising a question about the plausibility of the Hebbian learning rule that I mentioned. And in particular, the fact that in this learning rule, if the two neurons are quiet, you still have a potentiation of the synapse. And that's true. That doesn't seem plausible, although it's not completely impossible. However, this is not a crucial feature of this learning rule. You can modify the learning rule so that this will not happen. So only if at least one of the neurons are active, there will be change in the synapse. So there are even more biologically plausible versions of this learning rule, which have more or less the same properties. The one which I had here is simple because it symmetrizes the connections, and therefore you are guaranteed to have fixed points and so on and so forth. But it's fine. You don't have to worry about. I mean, this is the detail which you can relax and still it will work. Okay. So now let's go to more. Okay. So I mentioned at the beginning of my talk, and I want briefly to show here. We can ask from purely computational perspective, can we do better than this Hebbian rule? And indeed, one thing you can have here. So this is the Hebbian rule. There is something which is called pseudo-inverse rule, which has a decorrelating feature built into it. I won't go into details. It has a capacity which is fixed at 1, no matter what the sparsity level. So it's better here, but it's limited in the sparsity, in the sparse regime. There is even better learning rule, which is called the Perceptron learning rule. This also grows linearly with the sparsity measured in this 1 over f log f as our Heb rule, but the prefactor is much bigger. It's almost kind of optimal. And I mentioned this because these two learning rules, which if you are a machine learning or computational researcher, you'll recognize them. It's easy to implement and so on, but they have the feature that you have to recycle all the memories again and again until you get to the point where the memories are all encoded. So that violates this one-shot learning rule, which I mentioned. Okay? So, okay, so now I want to briefly address something which is tangential to memories themselves. It is related to memories, but it has to do with the memory representation. So all that I studied about now was, well, there is these vectors with some memory patterns that we want to store in the network. And now who created those patterns? So I said, well, there is some stimulus, which maybe is important, and there is attention or whatever. So the stimulus activate these long-term connections, long-term changes in the synaptic weights and then stored. So basically the stimulus imposes the representation on the network state during the encoding. But that would suggest perhaps that this is like a stimulus sensory representation. That turns out to be problematic. And that has to do with decorrelation, which I'll talk about in a minute, and then later on about the invariance aspect of representations. I'll also discuss it briefly later on. Okay, so I want to tell you one thing, that if you see demos, like I showed 1, 2, 3, 4, 5, and retrieval of memory in kind of Hopfield network with Hebbian rules, it almost always we cheat, because it will not work. If I did the honest Heb rule that I showed you without manipulating subtly where the ones are and where the zeros are, it will just fail, okay? Why? Because those fantastic one-time, one-shot memory learning rules are very prone to correlation. And this is more like what will happen if I want to store the image of brain and, I don't know, the image of circle, a set of words like this in a network, then I'm more likely to get something like that when I try to retrieve it. We call it spurious states, mixture states, and so on. And this well below the capacity numbers that I gave you. So even if you have, I don't know, 1,000 neurons or 10,000 neurons, you will not be able to store even 5 patterns if you don't do anything because of the overlap. So the issue of the format is important. So, by the way, the most sophisticated learning rule that I mentioned will deal much better with this. They have built in a decorrelation mechanism to not have this type of horrible problem. But if you just take the vanilla learning rule, the simplest Hebbian learning rule, you'll see it's frustrating, right? Because you cannot even store a few of those images in a network, even in a big network. So the correlations between memories, between patterns, are very important limitations. This is more kind of quantitative demonstration of that. So if I take this Hebbian network and I generate and I won't tell you how I do it, but generate patterns to store in the network, which have pairwise correlations, which are vary, but have this histogram. So this histogram of correlation, basically the dot product between pairs of patterns, and you can see that it's moderate correlations. It's around 0.1 and so on. Even in this case, even if I am 1/3 below the load, the capacity, and I start from a memory, I go to some other state. So the memories are no longer fixed points of the network, and the retrieval fails, even if I'm well below the capacity, even if the correlations are relatively weak. So these learning rules are nice, are simple, are fast, are plausible, but they have this problem. So this is a serious problem. How the brain might deal with it. And again, this problem is so striking that it's not a matter, okay, so the capacity will down by effect of something. It's really limiting the system in a very big way. Okay, so yes.
So you mean if we have more sparse network, we have less correlation, it's gonna
Okay, so this sparseness is the issue. So indeed, and that's what I'm coming to it now. So one way to deal with it is to actually generate sparse representation, and sparse representation tend to have less of this problem. So now I'm talking a little bit about how, so the general idea is that when you have this attractor network that stores memories, the memories that they store are not the patterns which are kind of the vanilla sensory representations, but have been pre-processed. And the simple pre-processing is by this kind of feed-forward network. So imagine this is the sensory representation, and this is our recurrent networks, but during encoding, in general, there is a transformation of the representation from here to here, and then this transformed representation are encoded in the recurrent connections and so on and so forth. So the interesting question is how to implement this transformation. In other words, if I take a sensory transformation here with correlations as not sparse and so on, what type of transformation by synaptic weights here will do the job of getting me something nice here? Basically, I want a decorrelation machine or randomizing machine. Randomizing is sparsifying. I want to take a data here which is correlated and dense, and by synaptic weights here to generate something here which is sparse and maybe large and not correlated, and something which will be very appropriate for storing in the network. Okay, so I can do it here. I can maybe be even more bolder and do it by multiple feed-forward stages and so on and so forth. But I just want to discuss the principle. So the question is, I'm sorry that now it's upside down. This is the sensory representation. This is what we call cortical representation. This is in our case, this will be the memory network. And the question that we ask is, how do implement it? What will be the nature of the weights that will do the job? Okay. Now, the simplest assumption, and there is some experimental evidence in some systems, which I won't discuss now in detail, is that these are basically random projections. So when you see in the brain something like that, a remapping of sensory data in a feed-forward manner, it looks like the connectivity is random. So each one of nodes here is basically connected at random to some nodes here and so on. So this will be great because this is something which is, again, doesn't need any learning, some sophisticated plasticity. We just have random connectivity between this network and this network. You impose sparsity here by threshold, spiking threshold mechanism. and that's it, and then you get what you need. So this is the question, whether actually this is enough. Okay, so here's the model. So in more detail, these connections, you can do it in sparse connectivity, but let's just do random Gaussian weights. This is good enough. And then these are these weights, feed-forward weights. Then each neuron here is summing the activity here. Then there is some threshold here, which imposes some sparsity level here. So that's a very simple model. And the question is whether this is good or not. So let's look at decorrelation. Let's look if random weights are good at decorrelation in the sense that if you take correlated data here and you do this and you sparsify it by this mechanism, you'll generate less correlated patterns. Okay, so the first surprising result that we had with Bakhtash Babadi and I, and it's published paper in Neuron, so you can look at the details, is that even if input patterns are random, are not correlated, actually the random synaptic weights will generate correlation, which was surprising to us. So the third thing we did is asking the following question. Suppose the patterns here are random, okay? Now what will happen if I just project them into this sparse high-dimensional layer? Will they still be uncorrelated? And the answer is no. It actually, the network will, this transformation generates correlation. Now this sounds counterintuitive, but I'll give you the very simple intuition why it is so. Let's imagine that there is no threshold here, that it was just linear. Then what will happen here, that if you have a small number of neurons here, and typically sparse and larger number of neurons here, all the patterns of activity here will just be lying in a subspace of a low-dimensional space in this large network. They all will lie in kind of hyperplane. Okay? Although you have high-dimensional network, but all the states lie in low-dimensional space because they originate from a low-dimensional origin. So even though you are randomizing, so to speak, you don't get rid of this. And you can see it here that this is what you expect in terms of pairwise overlap in the cortical representation, the amount of accidental overlap between patterns. This will be random. If this will be like truly random patterns in the expanded space, this will be kind of the distribution of overlap by chance. But in the projected pattern, you get much broader distribution. So you have high overlap. And the higher the dimensionality is, the lower the effect is. So again, the important point here is that we go from a low dimensional to high dimensional space, and we hope that this will create a high dimensional, like a filling, space filling representation, that one state will be here, another one will be here in this high dimensional space, but that's not what's happening. Basically, all the states of the network is lying in low dimensional tilted plane within this big network. So we are not succeeding to filling in the entire space. Why? Because we are just doing a linear operation with some threshold, but it's not good enough. Okay, so that's a problem. However, sparsity is helpful. So this is Q is this amount of correlations, and indeed sparsity is helpful. And so the sparser it is, the less there is some contribution, but it's smaller. The denser the network is, the more destructive this effect is. So again, I'm talking here correlations generated by the projection, not inherited by input correlation. So even if you have random inputs, in the next stage you will have some degree of correlations, and the degree of correlations will be suppressed by sparseness. So the sparsity does help in that sense. Okay, now what happens if at the input you have correlations? So on top of it you have input correlations. So imagine you have input correlations which are not zero. Now I'm talking about sensory inputs which are themselves correlated. Let's say that's an example, they have this level of correlations. And now in the next stage, you will see correlations. If it is not sparse, it may be bigger than the input correlations. If it is sparse, it will be improving. So indeed, if the representation is sparse enough, then you benefit by suppressing the input correlations. Okay? So that's the caveat. So although in this projection you generate extra correlations, but if the representation is sparse, this extra correlation may be rather small, and furthermore, you'll be able to suppress correlations in the input if the correlations in the input are strong, so like in this case. So if you are not sparse, you may actually induce more correlation than in the input. If you are sparse, eventually at some level of sparseness, you will do much better. You will decorrelate the input correlation, okay? So it is not a simple, it's not a simple story because of that potential harmful induction of correlations by the transformation itself. Okay, that's all. Okay, and I'll stop this. Okay, so that's about the correlations. I think Ed will tell us more about it in the context of hippocampus and dentate gyrus' possible role. Okay, let me now talk about invariant representation. So now the other problem that you may have is that, and Rodrigo alluded to it in his presentation, is that memory, at least in some cases, it's not the memory of the sensory stimuli as they are, but a more abstract version of them or invariant versions of them. And definitely when you try to associate different kind of concepts, you want to have a representation to start with, which is more concept-like, like brute force sensory signals. So it would be nice if the memory patterns at the level of the network that is encoding them as memory, that those patterns will be already pre-processed in a way that will get rid of some of the details of the physical instantiation of those objects or concepts or faces and so on. So this is a long and very important and hot topic in computational systems neuroscience, how to generate invariant representations. And one simple model would be to take, again, the same story here and to see whether this random weights into a high-dimensional sparse representation will have the property that if I represent the same object or the same concept of very different instantiations, you can think about it as noise, this will be filtered out and you will have here a kind of invariant representation of each one of these concepts. So you imagine that each concept is like a ball around a template, and all these points here are different physical versions of the same concept. So delta S is the degree of variations that you want to kind of squeeze out from the system at the input level. 0 is basically no variation. 1, I normalize it so that 1 is random, no structure at all. So imagine we start from inputs which have this structure. They're kind of clustered inputs. All inputs belong to one concept are coming from here. All inputs belong to another concept are coming from here. This is in state space, not in physical space, and so on. And basically we want to ask whether the next stage will take this entire sphere and represent it by one state. Will simply wipe out these variations. So we'll get invariant representation in the next state. That's the question, okay? Now, it turns out that unfortunately this random synaptic weights that I mentioned before are doing a very poor job. So here is the stimulus cluster size, the amount of variation in the input representation, and this is the amount of variation properly normalized in the output representation. And it's actually amplified. The more, and even worse, the more sparse it is, the higher the amplification of the noise or the variation is. So this is 0.01, 0.05, 0.01, 0.001. And for a given variance or noise in the input, you have an increasing variation in the output. The sparser it is, the worse, the more severe the problem is. Okay, so that's where the problem with all these nice models of projecting to high-dimensional space by random connections have to deal with this problem. Okay, so the question is, what can one do? I'll show briefly an answer, a tentative answer, but I must say it's an answer which is, I'm not satisfied in the context of memory. In other contexts, it may be fine. But here's our model, which we suggested in that paper which I mentioned. And this is the following. So that's not going to be random. What is going to be the following. So remember, the stimuli coming from here are clustered in state space, right? They're coming from these balls of concept or object and so on. So imagine I somehow generate, let's say I have P of this concept, okay? And each one of these concepts, I generate random sparse representation here. And I want all this ball of concept one to be associated, to map into one state of these random states in this layer. And how do I implement it? Again, by this Hebb rule. So I allocate random pattern here for each one of the concepts in the input layer. And I do Hebbian rule, so this is now hetero association. I associate representation here, this is the presynaptic representations here with the postsynaptic random representations here. And I do Hebb rule like this. And if you do this, then it's a remarkable improvement. So for instance, the correlations are again suppressed by sparseness, but way better and more efficiently than random projections. So for these parameters, this will be the amount of correlations in the network in the random projections, and they are completely suppressed, exponentially suppressed for moderate level of sparsity. So the degree of suppression of correlations or randomizing or decorrelation in this type of solution is much better. And moreover, the issue of suppression of noise or generating invariant representation is much better. So this is what happens in this Hebbian projection. So this is input noise, and this is output noise, or input variability, output variability. And the sparser it is, the more suppressed is the output noise. So, and again, you don't have to, 1.01% is already extremely suppressed. It's actually zero for moderate level of noise here. So basically, you get here an invariant representation that the entire sphere of inputs are projected into one state at the output, at this cortical representation. And you compare this and this, you see the enormous improvement of the operation of invariance representation gained by this Hebbian network. Okay, so why I don't like it, and I would like to you to come up with some ideas to help us. And this is because it is kind of look like a cheat. Why it is a cheat? I say I take random state here, and I associate it is with the Hebb rule with the templates here. But who is doing this? Who is putting or picking this random state for me to do the association? So somehow I need the mechanism to do this. Now, for instance, you can say the following. You can say, let's start with some random weights and start to do Hebbian learning on top of it by presenting examples from here and so on. It works, but it actually has it has severe limitations as well. For this purpose, for the purpose of generating good representations for memories. So, and in the literature, you will find papers that do that. Dented gyrus circuits, and they'll tell you that start and then do some Hebbian rule and something like that. I think there is a problem. I mean, it's an open problem, and Ed here has a solution. But I'm telling you it's a problem. Okay.
Well, why don't you make it into a competitive network? which is identical to that, except it has competition between the output neurons.
There is competition built in here.
Fine.
Already competition.
Well,
The
that's
result
the
that I showed you is even with the competition. That's what I'm telling you.
Yeah. But that's then what we call a competitive net.
It doesn't work. That's what I'm telling you.
But with this
No. This is on top of the competition. In the random network, there is this competition. This is with competition. This poor performance is with competition.
No, but what I'm saying is we understand a competitive network as what you describe as a pattern association network, but with competition between the output neurons.
This requires a lengthier discussion. I'll be happy to learn about the solution to this problem.
We've got till Friday evening.
What? Yeah, of course. Friday evening we'll have some. Okay. Let's switch to a few other topics before we get to the time limit. Forgetting. We heard yesterday how it's fantastic to forget. Wow! I don't know why I'm not happy about forgetting, but everybody else is. Okay, forgetting. Okay. Does this your genius forgot to forget or not? I don't know. Okay. But forgetting is indeed a problem. It is indeed a feature, not a bug. Okay, but there is something in it that you need the system to forget in most cases. Okay, why it is so? Okay, one reason we heard because this will free resources to force the network to synthesize knowledge, and I'm not questioning this. It's beautiful and it's important. But let's talk about memory itself. Here is what I told you about, right? So if you go above capacity, boom, the performance crashes, okay? The problem is the performance crashes for all the memories, okay? So it's silly, right? So imagine I'm here and I now go to ski and I experience 10 more interesting things to store in my memory. I cross this threshold and then I erase my disk completely. That's known as catastrophic forgetting in this type of networks. It's a feature of the distributed nonlinear. It's not an accident that it's not an exotic feature of particular model. It's a robust feature of this type of encoding information in synaptic connections. So it is a fundamental problem, an issue to be solved. All right. So the obvious or the natural answer is that what we did wrong was to give equal weight to all these patterns, regardless of when they were encoded in the network. We lost this time aspect of it, and we should reintroduce it. And then when we reintroduce it, we should find out that the more experience we have, we are basically erasing the old memories, okay, but keeping a window or keep a memory, keeping a front that, you know, for instance, all the time I store 1,000 recent memories. You know, the more I experience, the more I forget, but I always keep 1,000 memories in this. So that's the idea, and that works. Okay, and there are various ways of doing it. Let me just go. A simple way of doing it is so this is the same Hebbian rule, but now I'm adding weight decay. So instead of having this adding to the current or weight matrix, at every encoding instance, I actually reduce the magnitude of the current weight, all of them, by some factor 1 minus eta. Okay, that's called weight decay. So as I go along, I add this, but as I go along, I forget old ones because of this weight decay. So they're basically decaying exponentially to the past, the memory traces. So if you sum up this, you get this type of equation where t now is what we had p, right? The current matrix, okay, at time t is the same as before, but now the memories, memory traces, each memory trace come with its own weight. They're not all the same weight lambda. They have some own. And the memory trace is basically, this memory strength is a decaying, exponentially decaying function to the past, okay? So in the recalling time, if I'm at time t, and I'm trying to, and I look at my matrix W and ask, what is the memory trace of a memory which was encoded previously at time t prime, it will be reduced, the weight will be reduced by this factor. And again, the theory can show that tau has to scale with n, the number of neurons, or the number of connections per neurons, and it's kind of a capacity story now, but in terms of the horizon of forgetting rather than in terms of overall number of patterns. Yes, there was a question here? Yes?
Forgetting in reality means erasing traces or...
Yes, so I'll show you. Right, so if you look at the synaptic matrix, okay, and you ask how the memory traces decay, then they have this exponential decay. It's a graceful decay exponentially with this time constant, okay? However, if you now put it into the network back and you ask at any given time what will be the quality of retrieval of previous memory, it will be much more nonlinear, and that's what this plot shows. So, here it is. So let's look at this. This is with some time constant here, I don't know, 0.1 times n, and this is a retrieval quality where I start from the memory and I want to know whether I want to know whether I remain in that, whether it's still a fixed point. So this is the final state starting from the memory state at recent memories to old memories. And you see there is a rather sharp function. So I basically am not able to retrieve all memories, in the past where this is the time to the past, okay? But that depends on this time constant of the weight decay, right? So if time constant is longer, then I have more memory span. It's kind of more gradual, but I still am doing well and maybe better than this, so it's better choice. On the other hand, if the tau is too slow, then I get a total interference and I'm back into the catastrophe problem, and basically I have a familiarity trace, but not a good recall. I still have a familiarity trace, right? So it's not nothing, but the ability to recall the details is completely lost, okay? So there is an optimal weight decay, an optimal time constant for the decaying the synapses, which is kind of balance between interference between past and present memories and not cutting off too fast, okay?
It never decays to zero, which means you always have some information that it...
It's exponential, so never decays to zero, but I mean, it depends on parameter. It can be pretty low, and if it's too long, then it can be low. I would say never decays to zero. It also depends on the size of the system and the details of the dynamic update, as discussed before. Yes?
Shouldn't we consider the role of interneurons? For example, maybe this decay is done by them because maybe we forget something, and if we think about it...
It's possible, it's important. This whole topic is important. In my network, by the way, there are excitatory neurons and inhibitory neurons, which are all mixed together. It's an important question. What happens if you separate interneurons and excitatory neurons? It's another question. And indeed, it can be that they play different roles. It's all about discussions. It will take me away from this paradigm. Okay, good. So, optimal weight decay. Yes?
Could I just ask for a matter of information? So tau is not really a time constant. It's, it's a number of memories.
Yeah, of course, but tau is related, right? It's related to this eta. It's basically 1 over...
The point is it's updated every time you store a new memory.
Well, okay, so this is an important question, and I would like to learn it from you and other experts. So the question is whether, I translate Ed's question, whether this weight decay, which is the origin of this tau, is passive or active. Could be that there's a passive degradation of proteins and so on, and which is passive, or it could be active, that only when you encode new memory, you are forcing a decay. That's a very interesting question, and I leave it for now as an open question. It's very interesting. Okay, just one more remark. There is another way of generating the same functionality. And this is, instead of having weight decay, I don't have weight decay, but I bound the synapses. I say synapses cannot go above 1 or below -1, okay? So what happens is you start to do this Hebbian learning, let's say from 0. So the synapses go up and down, and then occasionally they hit the bound. Well, when they hit the bound, we basically lost the trajectory before that, all that you know that now you are 1. And then you keep on moving and so on. So basically, the memory now is limited by how many steps to take you to the boundaries, okay? So this is now, you can see, you can show that you get basically under some conditions similar exponential exponentially fading memory traces. And again, tau here is 1 over lambda. What is lambda here? I forgot. This should be lambda, not I'm sorry, eta is lambda, whatever. This lambda is this parameter, eta here. Now you see why it's previously this parameter was not important, but now it is important because it's relative to the bound. So if the change in the synapse is big, then I very quickly reach the bound. So I forget very quickly. If, on the other hand, the change in the synapse, each time I do a change, is small, then it takes many, many steps to reach the bound, so I have longer memory. This is why this encoding strength now, which is relative, which you should think about it as eta, the strength relative to the bound, is now playing the role of the time constant, and it behaves very similar. But it's an important alternative mechanism. Okay, now, besides forgetting, this is stupid and straightforward. You can say, why all memories, at the same time, let's forget about time now, have the same strength. Some of them are more important to me, are more salient, are more novel, I pay more attention. Okay, that's trivial to put into the system. All that you have to do is, in the encoding stage, have a stronger memory trace, a stronger amplitude attached, to the change in the encoding stage, and that works. So this is an example of this again, forgetting memory. This is now the time of encoding, okay, and the quality of retrieval going to the future. So this is not a normal memory with some weight decay. And now this memory is a memory that has been encoded with 20% stronger encoding strength. So you see that it's indeed survives longer. So that's very straightforward to put into this.
Do you get more neurons encoding these salient memories? Or
What?
Do you get more neurons encoding the salient
No.
memories? Or?
No, it's just the memory trace is stronger overall, and therefore it's kind of the competition to the attention of the neuron in the dynamics is they're doing better. They suppressed the other one and survive. Okay. Consolidation, wow.
Can I have a quick question about this?
Yeah.
So maybe this is just because of how it's plotted, but it seems to me like the salient memory just stays at near perfect performance longer and then basically immediately drops.
This has to do with what I said before to the question about forgetting. So if you look at the memory traces, they're kind of exponentially decaying. They're not like this.
Yeah.
They're exponentially decaying, okay? But if you now translate, you have these exponentially decaying traces, and you put it into the dynamics of the network, because the neurons are kind of highly nonlinear, they have this binary thing, then you tend to have this type of a threshold effect. If you use Edmond's neurons, which are analog neurons, it will give you a more graceful decay here. So this has to do with the neural nonlinearity in the dynamics. More questions? Yes.
If you put a lot of salient memories in the network, would they interfere with each other? Because
this is the interference, you see? This is what happens. If you are putting many, many memories and you are not forgetting, and the exponential decay is too slow, you basically, the past and the present are interfering so strongly that you basically get a poor performance. In order to get good performance, you have to shield the recent memories from the old memories by having exponential decaying traces or strong exponential decaying traces. And in that case, those memories are forgotten, but because of that, they allow these memories to be retrieved well. Okay, consolidation is another problem which I must say bothers me. And it's an important problem, and I think we need good solutions. What I'm showing you here is a solution. I would say it's not trivial, but kind of straightforward solution. What is the role of consolidation? How to consolidate memories? Now let me tell you, before I'm talking about the solution, what is the problem and why the problem is severe in type of memories that I'm discussing. Again, I want to start from the notion of distributed system. Distributed system means they have multiple memories kind of on top of each other encoded in the same synaptic matrix. Now suppose I want to consolidate a memory. Okay, well, so go to the memory and consolidate it, but the memory is not there anymore. What I have is synaptic matrix which has all the memories in it. If I had a modular, or more like a computer-like memories, where each memory is its own location, there is no problem. I can say, well, I want to do something there to stabilize that memory, and something there to stabilize that memories, and they do not interfere each other. But here I don't have those anymore as individual entities. I have a synaptic matrix which has everything in it. So what does it mean to, after the fact, how do I get access to a memory after encoding and consolidate it or reconsolidate it? That's the problem. So one solution is ship the memory somehow. Take some bunch of memories and slow process and coding into some other places which we nicely call cortex, and then there somehow synapses are below capacity and whatever, I don't know. Then stable, there is no forgetting, and you are below capacity and everybody happy. Maybe that's what the brain is doing. I don't think this is, but anyway, so that's the problem. How in a distributed system, if you are not doing it like shipping solution, how do you consolidate individual memories? How you get access to past memories, past encoding memories? And the straightforward answer, you just activate them as patterns, and you relearn them. So that's what I mean, consolidate by refresh or by rehearsal. So again, here is our decaying model as before, right? This was the previous model. But now imagine I take a memory which was encoded at time t, okay, and now I am reactivating it later on at time t plus r, where r is 1, 2, 3, whatever the refresh time is. It's not, it can be every 3 time step, it can be every 10 time step I refresh. So r is the kind of the periodicity where I refresh. So let's say I encode the memory, and then 10 times later, whatever 10 times mean, 10 days, 10 hours, 10 minutes, later I reactivate it and recode it. Okay, so this is this R. Okay, and every time I reactivate, what does it mean? I have the same decaying as before, but reactivate means that I re-encode, I add this lambda. Now, what I'm suggesting is that in order for this to make sense, first of all, R should not be 1, because that means that every time you just refresh your memory, old memories. So it should be, I don't know, 10 or 20 or whatever, should be some spacing between a consolidation, refreshing of individual memories. And secondly, that lambda should not be 1. I don't think that when I reactivate a memory when I am asleep or when I'm unconscious or whatever, it should have the same strength of re-encoding as when I attend originally attended to the same stimulus. It makes sense to me that it's not. So for me, consolidation makes sense under conditions where you don't have to recall the memory to refresh it every time step, and also you don't have to recode it in the same strength. So these are kind of parameters that you can now play and ask, does it work? And I'm not going to give you the answer, but this is something that you really have to store to find out regimes of parameters where it does make sense that by a little bit of gentle pushing of the memories that you reactivate spontaneously or whatever during sleep or during some other associations about it that you reactivate it, you do the re-encoding. Yes?
During the consolidation, would you say that the original, the consolidation stimulus is exactly identical to the original one?
It should not be. It should not be, of course. This is the simple, again, this is why this is a caricature of the process. It should not be. What you should have is reactivating a memory, which partially maybe is already corrupted. So it's not exactly the same, but you still have a chance to reinforce it to some degree. And now if the noise is averaged out, so if you do it many times, you may be able to kind of average out and get back what you wanted. But
so there you get your invariant part of the memory.
yes, but on the other hand, you can imagine that the noise might be averaged out over multiple, it depends. You can increase the noise, or you can have fake memories by this consolidation because you consolidate a corrupted version and now this is your memory. All these possibilities are there. Okay, this is kind of just a caricature of a simple story, yes.
So this is really important in the context of forgetting, because this gives you selective consolidation of the memories that you've actively recalled.
Absolutely. Okay, so here's the question. So I'll come to it. Okay, so that's, yes. I'll take 5, okay? Okay, very good. So here's the story. So here's the reconciliation protocol. And here is the effect. So this is a memory which is not consolidated. So this is again the future. This is an encoding time, and because of the fading, forgetting, and so on, it stays there only for this limited amount of time. But here is the reconsolidated memory. So it goes down, and then you go up and down. It's a kind of rather random looking event, but still you see it survives and can be survived indefinitely by this type of simple little refreshing of the memories. Okay, now the problem is, I think that's what Ed alluded to, and this story is in people talking about it and writing papers about it, but there is basically a tension between forgetting and consolidation. Because what I told you is that in these networks, forgetting is important, because otherwise when you go above capacity, everything crashes. If you don't want to get this, you have to have gentle forgetting. But now I'm telling you, well, no, you don't forget because you consolidate them. So the answer is you probably do both, but not all memories are consolidated, because if all memories are consolidated, you are back into the problem of not forgetting. So I think there is an interesting but largely unexplored, and that's what we are exploring now in more detail, a kind of a trade-off between retention of recent memories and consolidating. So basically what I'm doing here, I'm consolidating each out of, I don't know, 100 or 200 memories. Okay, so now the past memories are nicely consolidated, by the recent memories are now relatively fast forgotten because of too many resources are going to store these memories. So you can see this trade-off by just changing the parameters. If you're now allowing more graceful forgetting, so you have more of this part of the networks of the memories stored, the recent memories, you have now the consolidation is now kind of interacting with this, and you get this profile. So it's kind of a U-shape. The more recent memories and the past memories, the very past memories, are retained well in the network, but intermediate memories are gone. Now, I don't know whether this has anything to do with what people measure in psychology and so on, but I think it's an interesting feature of this type of a paradigm. So again, to think about consolidation as a process of a single memory is one thing, but then I think what we need to understand better is what is the effect on the entire network, where we have both fading or forgetting and consolidation working at the same time.
So this is an explanation for the recency effect, which means...
This might be recency effect, exactly. So that's, I think, would be interesting to talk about. So 3 minutes. Sequence learning, just briefly. So some people question the validity of this paradigm of memory, especially in terms of associative memory. You just, you see some partial something and you recall it, but there is no dynamic to it. It's not like recalling a story or recalling a movie or recalling a song. So I think there is a sequence generation aspect to memory, which is absent in the model that I discussed until now. But it's an old work, and there are many variations of that, and partly also models of hippocampal function, which basically are relying on the idea that in the Hebbian association, you should put delay. So presynaptic activity at time t, or memory event t, is associated through the learning rule with the next next memory. So it's not SIT, SJT, SIT, but SJT, SJIT plus, T plus 1. And I don't want to, actually we found out that we need slow and fast synapses. I don't have time to talk about it, but it works nicely. And again, you can see this is an example of storing a sequence of digits. So you start from partial Q, you go to 1, and then you start to transit to the next one. This is now the dynamics of the network, and it works nicely. Okay, fine. So I just want to close by addressing an issue which has not been, I think, until now addressed, but I think we should think more about it. This is, at least I believe strongly that at least computational neuroscientists should think more seriously about disease, about what the theories and models might tell us about the issue of disease. And so this is just a few words about this. So we can ask the following. You have this glorious network storing information, recall, and so on. What happens, how sensitive it is to damage? What happens if you take 10% of the synapses at random and just kill them? Okay, what will happen in the network? Now, it turns out that because of the distributed collective nature of the memory storage, it should have a robustness to that, right? It should have a robustness that things will fill in by other parts of the matrix of connections. And, okay, so if you try to do it in a naive way, and there are papers on it which I want to point out, that they tell you the following. This is the intact profile of memory, and then you take 25% of the depth of the synapses, and you find that almost nothing remains. And by the way, you don't see here the Ribot's law, but that's another issue. Okay, but why it is such a big effect? And the answer is, so what I'm telling you is the following, very briefly. What I expect in a distributed system, the degradation of memory will be linear in the number of fraction of synaptics which are lost in the network. So 25% loss of synapses, basically 25% degradation in the capacity of the network and so on. But that's not what you see. You see a big effect. And the reason why you see the big effect is because you simply lose synaptic activations and neurons stop to fire. And it's amazing how many papers talk about this in terms of Alzheimer's, and they don't realize that this is not the loss of information. It's simply neurons cannot be active. Information is hardly lost. So what I'm saying is that you have to be careful. You have to realize that in the brain there are homeostatic mechanisms that if there is some decrease in overall synaptic activities, there will be a homeostatic compensation that will keep back the activity level overall in the network. So if you put this into the system, then you see this kind of linear phenomena. If this is the intact profile, 25% is small change, 50% is larger change, and then at the end everything collapses. But the final message is that properly operating distributed network is robust to damage in the fraction of synapses. And when you see Alzheimer's patients and the numbers are 50% of the synapses are dead before you see something dramatic in their cognitive impairment and so on, the synapses, the remaining synapses are still able to, the system doesn't collapse, are still able to retrieve information in the system. And an important question is, what can you do to, even even the memories that you cannot retrieve, let's say 50% of the synapses are lost, so you retrieve those, the memory traces are still there in the remaining synapses. So it's not that everything was erased from the disk. So it's an important question is, what paradigm can you do in the network or this stage where so that the memory traces of the memories that are lost can be enhanced in some way to relieve to some degree the state of the network, namely the state of the human being. So by this I'll stop.